Thank you. It's always good to be back to ICTS. So I'd like to thank the organizers for the invitation and for this wonderful conference or workshop. So I'm going to talk about some applications of delta method to the theory of analytic theory of L functions and modular forms. Okay. So I guess yesterday you've already seen some circle method. So let me start with something that probably you have already seen. So we're interested basically in the function delta, which is Kronecker delta, which is a function from integers and text values 0 and 1. So delta n is equal to 1 if n is 0, and it is 0 otherwise. So it's just detecting the event whether an integer is vanishing or not. Okay? And that event is quite important in number theory, right? For example, if you're counting the number of rational points and varieties, you are trying to detect where some polynomial is vanishing or not. Right? Okay, so there is, so the circle method is about writing down Fourier expansions of this delta function. And one such version was given by Klosterman circle method, which goes like this. So there is a choice of a real number c greater than or equal to 1. So for any c greater than or equal to 1, he showed that delta n is twice the real part of the integral from 0 to 1, sum over integers small c going up to capital C, and then there is a sum over d, the collection of integers going up to small c plus capital C. So it's a double sum with the condition that C and D are co-prime. Okay. And then you have 1 by CD and E of n d bar C minus nx C D. Okay. Integral over dx. So this is, so you can, if you evaluate the right-hand side, and if n equals to 0, you can show that this is 1. And if n is not equal to 0, it is just 0. Okay, and the starting point, if you want to prove this, is the observation that delta n is the integral from 0 to 1 of E nx dx. Okay, and you may have already seen that Ez is a standard notation. It is e to the power 2 pi I z. Right? So for any integer n, delta n is equal to that integral. And then you split it up using the Faraday fractions. So you take all the Faraday fractions with denominator going up to capital C. So you'll have like small c going up to capital C. A is modulo C, so A is going up to small c from 1, and AC are co-prime. And then you split this integral into small Faraday arcs around the fraction A by C, E nx dx, where, so you're looking at Faraday fractions. So if you have one fraction A by C, then you have two neighboring fraction, one A prime by C prime and A double prime by C double prime, where C prime, C double prime are all less than or equal to C. And then this thing is the interval which starts from the midpoint here and goes up to the midpoint here. Okay, you can take this side open if you want and close. And this is the that segment. Okay, and then you do some change of variable, and you have to use some arithmetic information that you have about A prime and A double prime to see that it can, this will reduce to something like this. Okay? I'm not going into details, but I think that you'll see it in some other lecture. Right? Okay, so there is a couple of things about this formula here. So there is an integral, and there are two sums. Okay, and I'll call C the modulus. So C is going up to capital C. So capital C is roughly the size of the modulus. And D is running from capital C to C plus capital C. So D is running over all congruence classes modulo C. Okay, and it's roughly of size capital C, right? So you have 1 by CD. It's kind of balancing the number of terms over here, right? And then you have a trigonometric function over here. This is e to the power 2 pi I n d bar by C, right? And this is arithmetic because it only depends upon the congruence class of n modulo C and nothing else. So this part I will call the arithmetic part. But this part, it's not arithmetic. It doesn't, you cannot say that it depends only on the congruence class of n modulo C, okay? Because this is really a real number. Okay? There's no periodicity over here. And this I'll call the analytic part. Okay? So the phase function here splits into two parts. One part is arithmetic, another part is analytic. And then there is a sum over the modulus, and then there is an integral. Okay, the integral is over x, which is in the analytic part. And this is the arithmetic variable, which is involved in the arithmetic part. But in the Klosterman's delta method, this is also involved here in the analytic part. Okay, that is one big disadvantage in Klosterman circle method, that the arithmetic variable D is also involved in the analytic part. Okay. So our first target is to write down a modern version of the delta method, which is basically due to Duke, Friedlander, and Ivanich, which will separate the arithmetic part from the analytic part. All right? And the starting point for that formula is not this integral, but it starts from this basic observation that if the integer is 0, then it is divisible by all other integers. And if it is not divisible by 0, then there are only finitely many divisors. Okay. So we call it DFI, Duke, Friedlander, Ivanich delta method. You start with a smooth function. Don't have to be smooth. You start with any function. It's supported on the non-negative part of the real line, takes real values. Okay. And you want it to look like this. So it starts from 0, right? And it's vanishing here, and then it goes like this, and then it rapidly decays as it goes to infinity. Okay, so there's a rapid decay over here. I'm not going to specify what the decay is. You can think of it as an exponential decay. In most cases, W will be just compactly supported, so it is actually vanishing beyond a number, right? And you also want the sum over positive integers WQ, Q running from 1 to infinity. So it's normalized so that this sum is 1. You start with any such function, right? And then look at this sum. So you take any integer n and look at the sum over all integers 1 to infinity, but Q divides n. And here you take WQ minus W of absolute value of n by Q. Okay. And I'm going to claim that this is equal to delta n. Why is that? So if n equals to 0, I have to show that this side is 1. So if n equals to 0, this is vanishing because W0 is 0. So then you're just left with sum over WQs. But since n is 0, all the integers are dividing n, right? So you get this sum, which we have assumed to be 1. So when n equals to 0, it is 1. If n is not equal to 0, for any divisor q, n by q is also a divisor, right? So it will just cancel when you sum over q. Okay, it's a finite sum and they cancel. So it becomes 0. So the delta n is basically given by that. And now you can detect this event that q divides n by additive characters. So we have sum over q from 1 to infinity and 1 by q, sum over a modulo q. N by q. Okay, so this part, this is 0 unless q divides n, and if q divides n, this is equals to 1, right? And then you have wq minus w of absolute value of n by q. Yeah, at the end will be just, it's not necessarily non-negative, it's fine, it can take any. Yeah. But you have to put some differentiability conditions so that it is nice. Okay, so at the end, we'll be taking it to be, we'll take some interval C2 to C, and we'll take a smooth bump function supported between C and 2C. All right, so, and then what you do is, so A and Q, since they are summing over all A modulo Q, then are not necessarily co-prime. So you take out the maximum, GCD of A and Q's, and so, and then you just cancel that up, and then you are just left with this sum. So you have the sum over Q from 1 to infinity, 1 by Q, and then you have a sum over C modulo Q. So this is taking care of the GCDs. And then you have the Ramanujan sum. So I'm going to write it as A0 in C, right? And then we have this WQ minus W absolute value of n. Okay. And usually SM in C is the Klosterman sum. So it's running over A modulo C, co-prime with C, E of AM plus A bar n by C. So when you take M to be 0, then this part is gone, and you're just left with A bar n by C and with A and C co-prime. So that's the Ramanujan sum. So here, this is the it's a special case of Klosterman's. All right. And then since C divides Q, you can write Q as C times R. So I can write it as a double sum, a sum over C and a sum over R, running from 1 to infinity. 1 by CR is 0 in C, and then WQ, W of absolute value of n by Q. All right, and then this part doesn't depend on R, so I'll just have the sum over C outside into infinity, 1 by C, 0, C, and then sum over R into infinity, 1 by R, W of CR, should write here CR, CR, absolute value of n by CR. Okay, and we'll think of it as a function. So dfi, right, it does delta Cn. So it depends upon n and the parameter C, variable C. Okay, so now, yeah, so maybe it will be better instead of writing S0 and C, because I want to compare it with Klosterman delta method. Let me write this as, so that's the Ramanujan sum. Write it as a sum over D modulo C, O prime, E of D bar n by C. Okay, now you see a similarity, right? This one and what you have over here. All right. Then, okay. So when you're applying this delta method to a problem, you will basically have a collection of integers in certain interval, and then you will be interested in knowing whether an integer is vanishing or not, right? So for example, if you have a polynomial in several variables, then, and you're taking the variables in certain range, the size of the polynomial will lie in certain range, right? And then you are trying to see whether that polynomial is vanishing or not, right? So I'll be taking this integer n in certain interval from minus n to n, right? Because we're not interested in what's happening outside this range, right? And then I'll take W to be a smooth pump function supported between a parameter, say capital C, twice capital C. Okay, so it's something here, still satisfying this property over here, that the sum is 1. Right? So if you W is only coming the additive part. So if you sum over all the integers lying in between over here, so it's actually not really that high, it will be very low like this, right? So that the sum over them is just 1 at the end, right? So let's see. So if you want to make the sum to be 1, and if you have like roughly C many integers in between, so if you want it to be not really oscillating that much, you'll be taking the value to be 1 by capital C, basically. So roughly W is of size 1 by capital C, right? Because you want the sum to be 1. So, right, so if you look at this sum now, so this is of size 1 by capital C, this is like 1 by capital C, and this R sum is more or less converging because these are supported in dyadic intervals, right? So you'll have a sum over C. So I'm just trying to write down the skeletal part of this formula. So you have a sum over C from 1 to infinity, 1 by C, and then 1 by capital C. So I'm just going to write it outside. This is like coming from W. It's not exactly that, but you can put a 1 by C to normalize the size of W to be 1, right? And then we have a sum over D, modulo C, O prime, E of D bar N by C, and then something, sum over R, which has 2 parts actually. If you look at the first part, C times R has to be of size capital C, right? So here R should be of size capital C by small c, 1 by R, roughly. There's something over here that I'm ignoring, minus then 1 by R. And if this is between capital C and twice C, then here R will be between, since N is between minus N and N, so it will be N by C, capital C, right? And then something over here, right? But yeah, so what I'm trying to do, if I compare this formula with Klosterman circle method, the difference that is still there is that here we have a range for C, that C is bounded up to capital C. Here we don't have a range for C. I'm trying to find out whether we get a range for C, right? So if you look at this part, we're summing over positive integers, right? So this will mean that C can go up to capital C, otherwise it's vanishing. If you look at this part, this will say that C can go up to capital N by C, right? So here I can say that my C is going up to maximum of capital C and N by capital C. Right? So I have got a range. Right? Now C is up to me to choose, right? And if you want to choose it optimally, you will pick C to be equal to N by C, or C to be like square root of N. And in that case, that small c will go up to capital C. Okay? So my optimal choice, whatever that means, is C equals to root N. I usually have a twice square root of N or something. That's it, right? And once you have that, then this formula looks like this. You have a 1 by capital C, small c going up to capital C, 1 by small c, Ramanujan sum, U bar N by C, and then there is the analytic part, which is like 1. So we're still missing the integral over there. Right? And we're still missing this part, ENX by CD. So what we can do here, we can look at this function closely, and apply Fourier transform. Okay, so you can look at a Fourier expansion on that. So we can do a Fourier analysis. So we do a Fourier analysis here. And this will give you an integral over all real numbers. There will be the Fourier transform of this function, which I'm going to write as G. It will depend upon C and a real number X. And then, when you write it as a function of a variable, and that variable turns out to be just this one, right? Nx, it's not important, put a minus sign. I'm just putting a minus sign to match that sign over there, by C times capital C dx. Okay. Now, what you need to know here is what is the behavior of this function, G. Right? And for that, we have a collection of properties, which we can write down. The point is that this function G is almost like 1. Right? So GCX is almost like 1, but not really 1. It's 1 plus HCX. And this HCX is a big O. It's bounded by capital C by small c, and then small c by capital C plus absolute value of x to the power a, okay, for any a greater than 1. Okay, so what's saying? It's saying that if x happens to be a little smaller than 1, and small c is happening to be a little smaller than capital C, then by taking a very large, I can make it negligibly small, and then h is kind of practically 0, then g is actually 1. There's nothing left. Right? But if C is like capital C, which is a generic size, and X is like 1, which is generic size of X, this is not really 1, but it's almost 1, you see. You can also write GCX is also bounded by 1 by absolute value of X to the power A for any A greater than 1. So that means if X is larger than some number, it is really decaying rapidly. So I can truncate this integral roughly at 1. Okay, so this is a finite integral over here. So this is the second property. And the third property is about the derivatives of the function G. Okay, so this is bounded by log of C times minimum of 1 by absolute value of X, small c by capital C. Okay, and in the application of this delta method, these are the only properties that you really need. So you have this formula for, so this guy is my delta n. Okay, and this is it actually detects whether n is vanishing or not. For n in the interval between minus n to n, you have to pick your c to be roughly of size root n, and then you have this nice formula. Right? All right, now we compare this with the formula of Klosterman right here. Right? Okay. All right, now you see that the arithmetic part and analytic part are nicely separated. This is the arithmetic part. This is the arithmetic variable. It doesn't appear here. This is the analytic part. This is the analytic variable. It doesn't appear over here. Okay. So they are completely separated. So this is the arithmetic, and this is analytic, right? And okay, I can truncate this, say roughly from -1 to 1. It's not really true. Plus, I can write a negligible error term over here. And then that integral is the integral over x from 0 to 1, 0 to 1, and -1 to 1 are almost same. There's nothing different. Here, D is, so sum over modulus C is going up to capital C. There, C is going up to capital C, but that capital C is specific, that's root n. And D is of size capital C. So 1 by D over here is like of size 1 by capital C. That's the 1 by capital C that appears outside. Okay. So this can be compared with that, right? And so the cost that we have paid in separating the arithmetic part from the analytic part is this mysterious weight function G. Apart from that, everything is same, right? And this weight function has this nice properties. And in analytic number theory, this is all you need, basically. Right? So I'm mostly interested in applications of this. So today we're going to discuss some applications of both Klosterman formula and this delta method to some problems in analytic number theory. Yeah. So before that, I need to introduce some summation formula. And one of them is, of course, very well known. That's due to Poisson. Number one, Poisson. So it says that if you have a reasonable function on R, then if you sum over Fn, where n is running over all integers, this sum is exactly the sum over the Fourier transform of F over all integers. That's Poisson summation formula. So F is a reasonable function, and F hat y by definition, so it at least should be integrable. We'll have fx e of minus xy dx. That's my definition of Fourier transform. Right? And when you use this formula in analytic number theory, it usually comes in this form. So you will have a sum over all integers. Yeah. And usually you'll have a periodic function psi n. So psi is going to be periodic with period, say it's modulo some period q, right? And then, so it can be, for example, psi of n can be e of an by q, right? Or it can be like chi of n, where chi is modulo q. Okay, these are examples. Right? And then you have a weight function over here. So at the start, let's write it as capital Fn. Right? Now, if you want to use the Poisson summation formula to this one, you'll first split the sum modulo q, because psi only depends upon what n is modulo q. You'll have a sum over a modulo q, psi of a, and then you have a sum over a plus nq, where n is over all integers, right? And then we can apply, because this fits nicely over here with the formula. So I can apply Poisson to this one. So if I apply Poisson to this one, then I get sum over a modulo q, psi of a, right? Sum over all integers, Fourier transform, a xq e of minus nx dx. And then you do a change of variable. You call a plus xq to be y. So x is y minus a by q. And so dx is dy by q. So this guy basically reduces to 1 by q, sum over a modulo q, psi a, sum over all integers. And here you have fy e of minus ny by q dy, and then you have a na over q. Okay, and this part doesn't depend upon a, so I can take the sum over a and put it inside with this one. So I'll get a 1 by q, sum over n modulo n running over all integers. This is the Fourier transform of f at n by q. And then you basically have the Fourier transform of psi, a finite Fourier transform of psi a e of. Okay, so this is, if psi is chi, it's like a Gauss sum. Right? Okay, so that's our formula. Usually in application, what you have is here, you have some kind of oscillation. So it may be, there may be a phase function here. So Pn, and then n will be supported from capital N to 2n. So that's usually what happens to your weight function. It's not really a bump function, but it's a bump function times some oscillating function, right? And suppose that Pn is of size, say, k, right? So Pn is oscillating k. That means all the derivatives are of size k if you normalize it. Yeah, so it means it's taken to the power j. Okay, if that's the case, I can do a change of variable over here, right? So if you look at this integral, okay, so it will turn out to be n times the integral over r, and then this f will become wy e of p ny minus ny by q dy, right? And here, this is not oscillating, this is a bump function. Okay, so y is kind of separated between 1 and 2. So, and the derivatives are bounded by 1. So for this to survive, the derivatives of this should match the derivatives of this. So that will give you the range for n, okay? So here, once I have put this weight function over here, that will mean that n is roughly of size capital N, right? So that's the length of my sum over here. Now I'm looking at the dual side after applying the Poisson summation formula, and I'm trying to find out what is this length of n. What are the n's which are surviving, right? So here, n has to be of size, I'm sorry, I have to put ny, because I did a change of variable to take this n out, right? So n is going to match with k times q divided by capital N. Okay, so that is the size of the dual length. So this is a dual length. All right, and then this just becomes n by q sum over n of size k cubed by n. Maybe I should say going up to this size. And then you have this sum over psi a e of na by q, a modulo q. And then we have this integral for r. Okay. So that's what happened. Now, let me try to estimate this to find out what Poisson is doing to this sum, right? So suppose psi, okay, if you want, take psi to be chi n, right? So psi is like chi n, so it's a periodic function, it's a Dirichlet character. This is of size 1, right? So if you take the absolute value, this is trivially of size capital N, because small n is supported between capital N and twice capital N. And now if you come to this side, right, so this becomes the Gauss sum, right? And the Gauss sum has size square root of q. And what happened to this one? This, if you use stationary phase analysis over here, if you are able to do that, then this will be of size 1 by root k, right? So this integral is of size 1 by root k. right? And so if you ignore n equals to 0, because n equals to 0 is a special thing, then I have n by q, factor outside. I have kq by n many points of summation. The character sum over here is bounded by root q, and this is bounded by 1 by root k. Right? And so this n cancels out, q cancels with this q, and I get square root of kq. Right? So if you have that sum, which is trivially of size capital N, by applying Poisson summation formula, if you are able to get square root cancellation in this character sum, and if you're able to show the second derivative bound or stationary phase to the integral, then it becomes of size square root of k square root of q, right? So n becomes that. So this is something that I call saving. So how much have I saved by applying the Poisson summation formula? By applying the Poisson summation formula, my trivial bound from n has become square root of k square root of q. So my saving is n by square root of k square root of q. Right? So there's another way of looking at it. So you're starting with this sum, where you have a modulus q, that's the arithmetic conductor of this sum, and you have an analytic oscillation of size k. So the analytic conductor is k, right? And so the total conductor is arithmetic conductor into analytic conductor, which is q times k, right? And so the philosophy is that the dual sum will be the conductor by the initial sum, and the saving will be the length by square root of the conductor. Okay? So that's something that we should remember here. So the dual length is conductor by initial length, and saving is initial length by square root of the conductor. If you want, you can say this is also square root of the initial length by square root of the dual length. All right, that's basically what Poisson summation does. I'm ignoring the zero frequency because the zero frequency behaves slightly differently, and your saving may be slightly different. Right? But when you're taking a primitive character over here in place of psi n, there's no contribution from the zero frequency. So sometimes the zero frequency is not there at all. Okay. Yeah.
A little break about at the half to see whether this is for you a good time to take the break, or maybe you have a little thing to add before the break.
No, I think I'll take a break now because I'll go to another formula now. Yeah. So before that, I'll take a break.
Okay, so we have 5 minutes just and resume.
Yeah, good.
Okay, good. We'll resume. Thanks, Rita.
Yeah, thank you.
Rita, for continuing.
Yeah. Yeah. So, yeah, so I just explained what Poisson does to a sum. And the next step is Voronoi summation formula. So this is slightly complicated. I'm going to stick to, or I'll present a rough sketch of the proof only in the case of holomorphic modular forms. Okay, so I'll take F to be a modular form. So it's you can take it to be a new form or maybe just a cast form of weight K. Say modulus D, and we'll put an event typus ID, right? Okay, so if you take a matrix A, B, C, D in gamma naught D, that means C is divisible by D, then F of AZ plus B by CZ plus D is something, right? I hope most of you will know what it is, right? So that's the definition of modular form. There are certain other properties like the Fourier expansion at the cusps and all that. Yeah, and then you have a Fourier expansion at the cost at infinity. So if z, so z is a point on the upper plane, right? So if z is a sum over n from 1 to infinity. We'll take the normalized Fourier coefficients, lambda f n. Normalized, hence have to put a weight over here into the power k minus 1 by 2, right? And e z. So that's the Fourier expansion at infinity. And we are interested in the sum lambda f n e of n by c, and then we'll have a weight function. At the start, let's take it fn like before. And here the sum is from n equals to 1 to infinity. And take f to be supported, it's rapidly decaying up to some point. So, right, so that this sum makes sense. All right, okay. And so now we want to write down the summation formula for this, right? And there is an issue over here because this guy has a level D, and we have to see how the C is related to D, right? And so this is something that we'll assume that suppose the GCD of C and D is D1, and we write D as D1 times D2, then we assume that D1 and D2 are co-prime. Okay, otherwise, there is some problem while writing down the Voronoi summation formula. It's still possible, but it's a little messy. Right? Okay, so if we assume that, then of course, the Nibben-Tippers will split as a part modulo D1 and a part modulo D. Right? All right? Right, and then, yeah, so the formula will look like this. So there will be a chi of D1, A bar, and chi D2, C, to put a minus sign probably somewhere, minus divided by C. And then you'll have eta G D2 by square root of D2. So these are the eigen values of the Atkin-Lehner operator, but you can write it in terms of Gauss sum, which I will write in a moment. Then there is a sum over n from 1 to infinity. You don't really have f over here, but you have lambda f d2 n. I'll tell you what lambda f d2 is. E of minus n a d2 bar c d2. And then we have an integral fx 2 pi I to the power k, the J Bessel function 4 pi root nx by c square root of d2. Okay, so that's the formula. To tell you what this guy is, so G, I should, yeah, eta f d2 is basically the Gauss, the sign of the Gauss sum for chi d2. Okay, this is a sign of the Gauss sum by lambda f d2. Okay, if lambda f, this is a normalized Fourier coefficient at d2. If it is not equal to 0, then you can write eta f d2 as a Gauss sum by lambda f d2. If it is 0, then of course this doesn't make sense, and then it becomes a little complicated. Okay? And if you're interested, you can look at Winnie-Lee's paper or Atkin-Lee's paper. Okay, and what is, so FD2 is actually another modular form. Yeah, so, right. Yeah, so FD2 is another cast form of the same weight K, same level D, but some changes over here, I D1, I D2 bar. So the Nibin-Tippers changes slightly. Yeah, and so if you write down the Fourier coefficients, the normalized Fourier coefficients of FD2, then you are mostly interested in two cases, when n is co-prime with D2, and when D2, when n divides D2 infinity, that means all prime divisors of n are prime divisors of D2. Otherwise, any n can be written as some integer of this form and some integer satisfying this. And you know the Hecke multiplicativity, so it will split. Right? Okay, and here you have chi D2n bar lambda fn. Here you have chi D1 n lambda fn bar. All right. Yeah, I guess I did it. Okay. Okay, so that's a formula. Yeah, I just want to write down a short sketch of it. If you want to look at the details, you can look at this paper by Kowalski, Michel, Van der Kamp in Duke. Yeah, so how do you prove this? Yes, yeah, let me, because I really want to go to the application, so I'll just skip the proof, right? Okay, so excuse me for the moment. I'll skip the proof. Maybe I'll come back tomorrow and do the proof. It'll take some time, 15, 20 minutes. But let's look at the formula and let's see what it says, right? Okay. All right, so I want to find out two things, right? So first here, instead of Fn, I'll replace it again by Epn, W and N. Okay, again, this is oscillating like A, capital K. All right, and so trivially on this side, so N will be separated between capital N and twice N. So trivially, this is of size capital N. Now let me find out what is the dual length, effectively, and what is the size of this part. For that, I need to know some properties of the Bessel function. Right? And basically for here, what you need is that the Bessel function jk minus 1x is e to the power ix times a function w plus e to the power minus ix, conjugate of that function w, where this function w has size, so wx is a smooth, nice function, which is bounded by 1 by square root of x, or x to the power k minus 1, minimum of this two. Okay, so when x is larger than 1, then it is bounded by 1 by root x. And if x is smaller than 1, then it is smaller than x to the power k minus 1, where k is the weight of the form. Right? So that's what you need. So also you can look at the derivatives of that, and the derivatives also satisfy the same bound. So you can look at x to the power j, del x to the power j of this, and they have the same bound. So there is no oscillation in W, and this is the oscillating part in the J Bessel function. Okay, all right. So, to find out the length of the dual side, so let's plug in fx equals to that over here. So this integral for a change of variable becomes n, integral of e of p and y, right? And now I extract the sizes, the oscillation from the J Bessel function. So I'll get a 2 root n and y, c square root of d2, right? And then there'll be a smooth function, some wy, And so this Wi is different from Wi. All Wi, whenever I write a weight, I write Wi, but all the Wi's are different. So here this Wi means that Y is supported between 1 and 2. A nice bump function type of thing. Okay, and I need to put the size of the J Bessel function, which I will take to be 1 by square root of x, because it's smaller than the minimum, so I can take it to be smaller than square root of c d2 to the power 1/4 nx to the power ny y to the power 1/4. Right, so that's my integral. Okay, so the size is n times c square root of c d2 to the power 1/4 by small n, capital N to the power 1/4. And what about this integral? This is something that we already had when we looked at the Poisson summation formula, right? So we have to match the oscillation of this with this one. Okay, so that will give me the effective length of small n. So I should have root of small n, capital N, by c square root of d2 to be of size k. Right? And so I'll have n to be of size ck square d2 by n. Okay, so that's my dual length. Right? Okay, and let's come back over here. So here we have the modulus to be c, right? And this guy is oscillating like k. Right? Now, this also has a level, and the level is d1 times d2, where d1 divides c. Okay, so the d1 is kind of taken care of by c. So when you, since it's a GL2 Fourier coefficient, this modulus and the amplitude of the phase function should get squared when you compute the conductor. So the conductor will be c times k whole squared, and then whatever is left out here, so that is d2, because d1 is already taken care by c. So the conductor here is d2 ck square, right? And so that's what we have written here. So it's the conductor by the initial length, like what we had there. So it's a conductor by initial length. So the dual length is conductor by initial length. And now let's compute the size, what is the trivial bound for this guy, right? So we have a 1 by c and 1 by square root of d2. Right over here. 1 by c square root of d2. And the length of n is this. So n is going up to ck square times d2 by n. And then lambda f d to n is like 1. That exponential thing is 1. And this integral is n. So I'll put an n over here, times this guy, square root of c d2 to the power 1/4, n to the power 1/4. And then here, from here, using second derivative bound or stationary phase, I'll get a 1 by square root of k. Okay, and if you do the computation, you have to do the sum over n with this n to the power 1/4, right? And then if you compute, you will see that this side is of size square root of the conductor. So we'll get this. This is of size ck square root of d2. Okay. So again, the saving is we started with the sum of length capital N, and trivially it is bounded by capital N. And when you come to this side and estimate it trivially, it is bounded by square root of the conductor. So again, the saving will be n by square root of the conductor. So so the nature of summation formula is always the same. If you look at the Poisson summation formula or the GL2 Voronoi summation formula, okay, the dual length is given by the conductor by the initial length, and the saving is given by the initial length by square root of the conductor, right? Yeah. So I wrote down this for holomorphic modular form. There is another formula for mass forms, which has the same kind of structure. Instead of the jk minus 1, here you have a Bessel function with imaginary argument or imaginary weight, whatever it's called. And then you have higher level Voronoi formula, right? So let me just go into an application. And the application that I want to start with is actually a GL3 application, right? So, instead of the GL2 Voronoi formula, I'll be applying the GL3 Voronoi formula over there, right? And when I apply it, I will tell you what is happening over there, right? It will look almost same like this, with a, when you have this knowledge that how much you're saving and how much is a dual length, then you can really write the Voronoi summation formula in the skeletal form. It looks like this. So n is of length n, we have lambda fn, E of an by c, and E of pn, and pn is oscillating like k. Then it is just taking us to a formula, to a dual length of size ck square d2 by n. Instead of lambda fn, it is slightly different. There is some sign over there, which will involve the Gauss sum and other things. And then here you'll have a E of minus a d2 bar n by c. And then you have this integral, and the integral will be basically E of p n y minus 2 square root of n y by c square root of d2 dy. Okay, and here y is like 1. Okay, I'm not writing down the explicit weight factors that will appear over here, but the weight factors that appear over here will be such that the trivial size of that side is square root of the conductor. Okay, so you know how to write down the weight factors. So the skeletal form is that you start with this sum, and the GL2 Voronoi transforms it into this sum, right? If you are just looking at level 1, which is the nicest case possible, there is nothing to worry about over here, because whatever was outside is only depending on having a level. If the level is 1, there is nothing, there is no chi d1, there is no chi d2, so this part is just 1, this part is just 1, f d2 is just f, d2 is gone, and it looks really nice. So if you're looking at d equals to 1, so this is a level 1 case, then the formula is just, is going into n of size ck square by n, lambda fn, E of minus a bar n by c, an integral, a smooth integral, exponential integral e n y minus 2 n n y by c. That's GL2, right? If you stick to level 1 and you want to look at the GLD form, instead of GL2 to GLD, and here instead of lambda fn, we'll be having the Fourier coefficients of the form. So let the form be pi. Right, so this is the nth Fourier coefficient of that. Then what changes over here? So so let's write it this way. So instead of this 2, you will have a d over here. You will not have that. You will have a Klosterman sum, which will be, what is that, d minus 1? D minus 1. A bar in C. Okay, so in D equals to 2, it reduces to this guy. You may put a minus sign if you want. And here, instead of 2 over here, you have to put a D. And instead of this to the power 1/2, you have to put to the power 1 by D. Okay, so structurally, the skeletal part is just this, right? And what you need to know is how much you're saving. The saving is square root of the initial length by square root of the final length. Okay, and what is the conductor? Conductor is C times K to the power D, because it's a GLD form. Right? So that's the Voronoi summation formula. Yeah. A pi n is, yeah. So is A n 1, 1, 1. You can put some things over here, but yeah, so this becomes A pi n bar or A 1, 1, 1, 1 n. Okay, yeah, it's a little different. But basically, that is the structure. You need pages to actually prove the whole thing. But essentially, that's it. All right. So now let's go into applications. So I'll start with an application where actually the Klosterman delta method works. Okay? So I'll be interested in a GL3 L function. So pi will be a GL3 Hecke-Cast form, right? And we have associated L function to it, L is pi, which is given by our Dirichlet series, A pi n by n to the power s, 1 to infinity. If you take the real part of s sufficiently large. And this is also given by an Euler product of degree 3, so P prime, 1 minus A pi P. It's slightly difficult to write down all the terms, but I'll have a degree 3 function, e to the power s, so write it as alpha pi P inverse yeah, 1 minus maybe I'll just yeah, keeping in mind what's going to happen next. So I'll just take j running from 1 to 3, 1 minus alpha pi j p at p to the power s. Okay, and so these are the Satake parameters, the local parameters, which is associated to a GL3 by Hecke mass form. Anyway, it has analytic continuation and functional equation and all that. And so if you are comparing, if you know about Riemann zeta function, this is analog of the third power of zeta s. Right? But of course, it doesn't, if you look at zeta s to the power 3, then you are looking at the Fourier coefficients at D3n, or the Dirichlet coefficients at D3n, which is quite easy to analyze. The D3n's are replaced by A pi n's, which are much harder to explain. These are, of course, related to some very non-trivial representations. Right? So it has analytic continuation and functional equation. And yeah. And the conductor, so I'm just going to fix pi and change s. So s is going to be half plus it. I'm interested in understanding the size of L half plus it pi as t goes to infinity. As t gets larger, what is the size of this? Okay, and the Riemann hypothesis, or the Lindelof hypothesis, which is a consequence of the Riemann hypothesis, says that this does not become too big, so it is bounded by t to the power epsilon for any epsilon positive. Right? So that's the Lindelof hypothesis. But what you can prove quite easily is that this is bounded by d to the power 3/4 plus epsilon. Yeah, that's called the convexity bound. Right? And the problem here is to reduce this 3/4 to something smaller than 3. Yeah, that's called subconvexity. Right? The conductor is t to the power 3, right? Because it's like if you look at the Riemann zeta function, the conductor is just t. And then if you're taking the cube of that, it becomes t cubed, right? And so that's, so the conductor to the power 1/4 is the convexity bound, that is t to the power 3/4. Okay, so to get something better than this, one way is to look at the approximate functional equation. And the approximate functional equation replaces L12 plus IT pi by a finite Dirichlet series, which looks like A pi n to the power half plus IT, basically, where n goes up to square root of the conductor, and the square root of the conductor is square root of t. Okay? So it's t to the power 3/2. Okay? So the approximate functional equation says that this guy can basically be replaced by something like this. It's not completely true, because there will be a dual part, because it comes from the functional equation. But roughly, if you want to bound this, you need to bound this. And if you bound this trivially, assuming that A pi n are bounded by 1, which is the Ramanujan conjecture, which is not known, but on average it's known, then if you replace this by 1, then n to the power it you can ignore. 1 by square root of n, you get t to the power 3/4, which is the convexity bound. So the trivial bound here gives you the convexity bound. And you need to get something better than the trivial bound. So you need to use the oscillation of n to the power it over here to get cancellation in this sum. Yeah, so here I'll be using another of Keshav's. Thank you. I'll need one more today, I think. Okay. So I'm interested in A pi n to the power it. Forget about the square root of n, because square root of n, you know what size is, square root of n. So I'm going to take n roughly size capital N. So if small n is smaller than t to the power 3/2, you can use the trivial bound and it's good enough. So I can take my n over here. So this means that I have a nice smooth function over here, which I'm going to ignore, right, for notational simplicity. And the n is roughly of size t to the power 3/2. Actually, in our case, it will not be that important to have n to the power it. Actually, you can replace it by more abstract phase function Pn, which is oscillating like small t. Okay, a more general problem will be to look at the exponential sums twisted by a GL3 Fourier coefficient, and suppose that the oscillation is like k, and to find out how large k can be allowed to have cancellation over here. So that will be the more general problem. Okay. In this particular case, we are looking at the k in the case where k is of size t and n is of size t to the power 3/2. Okay. So here we'll apply the delta method. So let me write it by n. So maybe n to the power it. Let's do it with this. Okay, so the first step is the most silly one. You separate the oscillation of A pi n from the oscillation of m to the power it. And this is where exactly you use delta. A pi n m to the power it delta minus m. Right? because delta n minus m is 1 when m. So now I just want to replace this formula. I want to apply the Close-Terman-Circle method to this. So I'll just take this formula and replace it over here. Okay. Forget the twice real part. That means this plus its conjugate. So I have this integral and this sum. And then I'll be applying the Voronoi summation formula and the Poisson summation formula and try to find out how much we are saving from there. If you do it blindly, all right, okay. Yeah, okay. Okay, let's try to do that. Yeah, so let's replace it over here. I will not choose, I'll just keep my choice for C flexible at the moment. So my C is going up to capital C, right? So this is now, there's an integral 0 to 1, and there is C going up to capital C, and the D going up to C plus capital C. C and D are co-prime, that's the star, 1 by CD. And then I have a sum over n of size n, a pi n. Okay. So here in place of n, I have to replace it by n minus m, right? So the n part will be n d bar by C, d of nx by CD, right? And then I have the sum over m of size n, m to the power it, e of minus m d bar by C, e of mx by CD. Fine, right? So here now I can use my Poisson summation formula, and here I can use my GL3 Voronoi summation formula. All right, so what have I achieved using the circle method? I have separated the oscillation of a pi n from the oscillation of m to the power it. The oscillation of a pi n is in the n sum, and the oscillation of m to the power it is in the m sum. So they have been separated. What is the price that I have paid? The price is that I have introduced an extra sum n. Right? Whereas here my trivial bound was n, my trivial bound over here is n squared. Okay, this CD balances this sum. This is some integral from 0 to 1, so it's balanced. So my trivial bound is n squared. So I have to save n, and anything extra beyond n will give you a non-trivial bound. Okay? So my job over here is to save n to the power 1 plus something. All right. Okay, I apply Poisson summation over here. This is my arithmetic modulus is C, right? And the analytic oscillation, here it is oscillating like T, right? And here it is oscillating like M by CD. X is like bounded by 1. M is of size capital N, and C times D, if C is generic, is of size capital C square, right? So generically, this guy, so the generic size is N by C square, which I'm going to take call capital K, okay? This guy also has generic size K, right? But I'm going to take K, the oscillation here, to be smaller than T. So K is smaller than T, right? So now, what will be the dual length? So what is the conductor of the M sum? Yeah? Try. So the arithmetic modulus is C, and the analytic oscillation is T and K is smaller than T, so it's T. So the conductor is C times T, right? So what will be the dual length? Conductor by N, so CT by N, right? So when I apply the Poisson summation formula, the M sum, it gives me a sum of size CT by N. I'm taking the generic size of small c. And, right? And what happens to this when I do the Poisson summation formula? Right? When I apply this, when I apply the Poisson summation formula, I'll have Fourier transform of that. So I'll have alpha modulus C, E of minus alpha D bar by C plus M alpha by C. Right? And that will mean that M is congruent to D bar modulus C. So this will imply that D bar is congruent to M. So I'll have this information also, congruent to D bar. Okay, otherwise, the Fourier transform of the arithmetic part will not survive. And then I have the integral. Right? So I'll have an integral which will look like ny to the power it e of m x ny by cd minus m ny by c. So that's my choice. I'm assuming, so I'll pick my c at the end. I'll pick my c in such a way that this k will be smaller than t. So that's my choice for c. Yeah, because Klosterman sum comes with that choice. All right. So now this part is oscillating less than this part. So the oscillation of this should match this. Okay, that's why we get m to be ct by n. Right? And so by stationary phase, you can use stationary phase analysis over here and explicitly compute what you'll get. Let me tell you what you get by explicit computation. Okay. So we'll have here T by 2 pi E Q M to the power IT. Okay. And then you have a E of minus X by Q. So C. In this case, it's not C, it's D. 2 pi. Plus there will be other terms also. You know what, I'll not write it down explicitly. It has that part, and then there are other parts also that I'm not writing down. Okay. But here, the oscillation is of size capital K and not T, because the T part is over here. Whatever remains over here oscillates like K. Q is C. Yeah, that's yeah, because I use different notation over here. That's my confusion. Is that my time? We'll have 5 minutes, okay. Right. Okay, and so that's my Poisson summation. Now, if I use my Voronoi summation, so what is my conductor here? So the arithmetic modulus is C, and this is oscillating like K. Okay? So my conductor will be C times K, and because it's GL3, it will be CK to the power 3. So I'll have here CK, or let me write generic size to the power 3 by N. And I'll have over here A pi N bar, and then I'll have S D N C. Okay, so this is the KL3, KL2 that I was writing down there, KL D minus 1. So that's the Klosterman sum. That is the transform of this arithmetic part. And then I have E of minus N X Ny by CD plus 3 N y to the power 1/3 by C. And here also you can use stationary phase analysis to write it down explicitly. Right? Yeah, so that's the dual length. That is the structure. And now you'll see why the Klosterman sum, Klosterman circle method works here. As I said, the main disadvantage in the Klosterman circle method is the D appearing both in the analytic and arithmetic. Because it's an arithmetic variable, it should be appearing over here. It also appears over here. So that was the problem. But here, D gets determined because one part is just GL1. We're using Poisson summation formula, or D is getting determined. Okay? So D is a unique number in that range, which is congruent to M bar modulo C. Okay? So this D is uniquely determined. This D is also uniquely determined. Right. So now, so now let's see how much you have saved. In the Poisson, I have saved actually N by CT square root. Right. So that's the initial length by the square root of the conductor. But this gets determined, so there is an extra saving of square root of C. Okay? Because this is like we have done the sum over D. So that's my extra saving. How much have I saved over here? I have saved N by Ck to the power 3 by 2. So Ck to the power 3 was the conductor. And then I have to do my X integral. Okay, I didn't write it down explicitly over here. This depends on X and oscillates like K. This after stationary phase analysis, you can write it down the stationary phase explicitly in terms of X, and it will be also oscillating like K. So you'll be saving a square root of K because the X integral will be of size 1 by root K. So that's how much you have saved, right? So cancel C, square root of C. The N is something that you wanted to save and something extra. I have an N, you have a square root of T, you have a K, and you have a C to the power 3 by 2. So this is how much you have saved. Right? But you'll see that since this is not enough, okay, your choice for C cannot be that small that this will be smaller. I want this to be smaller than N so that this becomes larger than N. But this will not happen because I'm going to take my K smaller than T. So if I want K to be smaller than T, C has to be sufficiently large. And when C is that large, this cannot be smaller than capital N. So we are not yet done over here. Okay, so this is then followed by a Cauchy inequality, where you take the N sum outside. Okay, so you're left with an N sum. We have an M sum. The D has been determined. We still have a C sum. So we have taken care of the X integral by stationary phase. We have taken care of the D sum because D is congruent to M. All right, so the N sum is free. That is this, Ck cubed by N. And then inside, I'll put the I'll put the C sum, and I'll put the M sum. And then I have here S of minus D, but D is congruent to M bar, so that is minus M bar N C. And then I have my C by M to the power IT, but it does not depend on N. And then there is a phase function which depends upon N, but it's oscillating like K. Right, so now we apply Cauchy's inequality, the square over here, and we open the absolute value square, bring in the N sum, and apply Poisson. So I'll get 2 copies of Klosterman sum. We have 2 copies of modulus, C1, C2. And I have this 2 copies of this oscillation, but this is an analytic oscillation, so the oscillation will not increase, it will remain K. But the modulus will become squared, so C1 times C2. So when the modulus is C1 times C2, how much are you saving from Poisson? Saving from Poisson is the length by square root of the conductor. The conductor is C1 times C2. So square root of that is capital C, and K square root of that is S. So this is how much you save. C square A to the power 5 by 2 by N. Okay, as I said that this saving is in the non-zero frequency. Then you have to look at the zero frequency. But the zero frequency in this case is equal to the number of points of summation in the diagonal. Okay, and that is the number of C's that you have and the number of M's that you have. Okay, and that I'll call the diagonal length. So diagonal is number of C, which is C, and the number of M, which is CT by N. Okay, and so K by definition is N by C square. So you can replace K, you can write it in terms of N. So it's C square by N, or N by C squared is K, so it's K to the power 3 by 2. And this is T by K. You can equate these two to get the optimal choice for K. Right? And that will give you the optimal choice for C. Okay? And you'll see that in that case, that's choice for C, because you'll have something in K, the optimal choice of C is not square root of N. So here in the Klosterman circle method, you will not be taking your modulus to be square root of the size of N. In the delta method, you're kind of forced to take C to be square root of N, right? Here, you're not, at least in this form of the delta method. Right, and yeah, so finally you have a N, the N by C squared is K, C root C by root T, and then I have this extra K to the power 3 by 2. This is equated to this one, right? Or you can take T by K squared. Right? So that we're putting a square root. This is how much you save here, but we did a Cauchy. So when you go back, I have to take a square root. Okay? This cancels out N C by K square root. So now this is larger than N if C is larger than K. So is that the case? When you equate this to, K is T to the power, so K to the power 5 by 2 is T, K is T to the power 2/5, right? And then what is my C? If K is T to the power 2/5, which is N by C, and N is T to the power 3 by 2 by C square. So C is T to the power 3/4 minus 1/5. So I have to check whether 3/4 minus 1/5 is that. Whether T to the power 3/4 minus 1/5 is larger than T to the power 2/5. Is it true? This happens if and only if 3/4 is larger than 3/5. Okay, I wrote 4/5. That's fine, right? Okay. So it works there. So you have a choice of C, and that will give you subconvexity. So that's an application of the Klosterman delta method in analytic theory of L function. So I'll stop with that. So tomorrow I'll give an application of this delta method, a couple of applications of delta method. And after that, I'll introduce the trivial delta method, and I'll show that though it's trivial, it works remarkably well in many cases. It gives you the Weil bound or the Burgess bound, which is the kind of the strongest bounds that are known in case of the GL2 forms. And I'll also introduce the Utila circle method. All right, okay, thank you.
Okay, thank you very much. Ritabrata. Are there questions or comments or remarks? Hello. So if not, thanks again.